Okay, X-ray machine. So you need to know the parts, what they do, and the energy conversion for them. They're also called a hot cathode X-ray machine, or also a Coolidge tube, named after Coolidge, who discovered it. And I'll post a video with Coolidge actually explaining how his machine works after this. So first off, the diagram looks a little bit like that. It might look complicated, but it's not really. Okay, now if we take a look at the left-hand side, it says low voltage, and that low voltage is, there's wires up to the point labelled A. That's a heating filament. Also, on the left of the heating filament, there's a moon-shaped object. So the heating filament will heat that moon-shaped object, which is called a cathode, and thermionic emissions will occur at the cathode. We've seen something like that before. Now, between A and B then, there's a very high voltage, and what that voltage will do is accelerate the electrons across, and those accelerated electrons will strike B while moving at a very high speed. B is the anode, it's also referred to as the target, and it's typically made from tungsten, which is a metal with a high melting point, which means that the electrons can strike it, it can heat up to high temperatures, and then when it heats up to high temperatures, the X-rays are given off. And the X-rays are those dots there in the middle that are shining downwards in a kind of triangular shape from B. Now that's basically how it works. The rest of it is shielding to prevent any X-rays escaping out so that the user isn't exposed to X-rays all that much. And then the X-ray machine is contained within a vacuum so that there's no particles to get in the way of the moving electrons. And that's it. So it's basically thermionic emissions, free electrons from the confines of the cathode. The electrons are fired across, they strike the anode target, that heats up the target, X-rays are produced, and then the rest is just shielding and a vacuum. So this is from the notes. Another explanation of it. So thermionic emissions occur at the cathode, that's the first 2 points. They're accelerated across with the high voltage, point 3. The kinetic energy gets converted to heat, and it must be removed with a coolant. So when you look at the textbook, you'll see that behind B, or to the right of B, there's a circulating coolant to keep the anode target cool. Then what happens is the heat from that causes electrons in the atom to be bumped up to higher energy levels. They fall back down, give out X-rays, and they're emitted in all directions. And then the final point there, number 7, says the shielding has a little window in it, and the window then allows you to focus the direction that the X-rays are traveling. Okay, so if this was an X-ray of your teeth or a bone, what you would do is you'd put your teeth or your bone below where that dotted triangle, those X-rays are being given off, and then below that further, you'd have a sheet of photographic paper, and that would allow the dentist or the medical examiner to determine whether your bones are cracked or your teeth are damaged or something like that. Okay, the energy transfer that takes place. You'll be glad to know that it's identical to the cathode ray tube. So the electrical energy from the high voltage gives the electrons kinetic energy. So that means we'd have electrical energy equals kinetic energy, and we can use the same 2 formula as well. Okay. There's another energy conversion that takes place after that, and that is the kinetic energy of the electrons is transferred to heat energy in the tungsten, and less than 1% of the kinetic energy is converted to X-rays at the end of the energy conversion there. So very little of the electrical energy appears as X-rays, so it's a very inefficient process. Let's do a calculation. It's an identical calculation to the cathode ray tube. So high voltage is applied, calculate the energy given to the electrons. So the electrical energy is converted to kinetic energy. We're just looking for electrical energy right now. So multiply the 2 of those and we get electrical energy like that. The speed of the electrons as they hit the screen then, we can leave that value equal to 1/2 mv squared. And that works out as 3.2 by 10 to the 7, I think. Now, I'm going to add on a little bit here. If you're told that only 0.05% of the kinetic energy of the electrons creates X-rays, what is the total combined energy of the X-rays being produced? Or what is the energy of the X-ray being produced when one electron hits it? So in this case, the energy in the form of X-rays is 0.05% of the energy of the electrons. So when you convert 0.05 to a fraction, you divide it by 100 and then you multiply by the energy of each electron. And that gives you 2.4 by 10 to the minus 19 joules of energy from each electron that goes into producing an X-ray.